And for the final talk of this session, it is my great pleasure to introduce incoming Kavli Fellow, Iryna Butsky. And Iryna is going to be telling us about what scatters cosmic rays in our galaxy. So take it away, Iryna.
Thanks. Hi, everyone. My name's Iryna. I'm actually an incoming Hubble Fellow. And in the next...
Apologies.
Oh, no worries. And in the next 5 minutes, I'm going to tell you about all of my work with cosmic rays at a very, very shallow level. So I come from a background of galaxy simulations, and I've spent a lot of time in the last 5 or a little more than that years thinking about implementing cosmic rays in galaxy simulation codes and then running those simulations with cosmic ray stellar feedback to look at how cosmic rays affect the structure of the circumgalactic medium. And one of my very favorite kind of results that keep popping up in these simulations, and it's not just in my simulations, this is also coming up in simulations of basically any group that runs galaxy simulations with cosmic rays, is that the circumgalactic medium around, asterisk, low redshift L-star galaxies might be supported by cosmic ray pressure. And that does a lot of weird things to the state of the thermal gas, primarily the state of the cold gas, which you can have like very kind of large reservoirs of low density cool gas in your circumgalactic medium. And that has implications for observational signatures, kinematics, has a lot of implications. But the thing is, we don't actually know whether the circumgalactic medium is supported by cosmic ray pressure, or maybe if cosmic ray pressure is negligible in the circumgalactic medium. And that's because it's very hard to constrain observationally. And theoretically, these models are very dependent on cosmic ray transport, which is extremely underconstrained. And so if you look at this toy plot that shows the average cosmic ray transport rate, and I should add that this is for low energy cosmic rays, so around GeV, as a function of distance from the galaxy center, most of our observations really only constrain the cosmic ray transport rate in the local ISM. And it's not at all clear how to extrapolate those transport rates to other regions, either the ISM of other galaxies or the circumgalactic medium. And there really are transport models that can reproduce all of these observations in galaxy simulations that then diverge by many orders of magnitude in their predictions for the transport rates in the circumgalactic medium. And so recently I've been kind of going about constraining cosmic ray transport rate in a couple of different ways. One has been by directly trying to constrain the cosmic ray transport rate in the circumgalactic medium, and I should say indirectly because I'm not actually measuring those cosmic rays. But this plot is from a recent paper where we came up with an analytic model. I can take a handful of observables of the circumgalactic medium and convert it into a lower limit for the average transport rate in the circumgalactic medium. And when we applied this to the COS halos sample, we found that, I can't see my pointer, that this already rules out models in which the cosmic ray transport rate does not increase in the circumgalactic medium. And so this is a really exciting first result, but there's still a lot of work to be done. And especially FRBs are really primed to help us get a lot more data on this. But the other way of going about constraining cosmic ray transport rate is by thinking about the actual microphysics of how cosmic rays are scattered on AU scales that then leads to this galactic scale transport rate that we plug into our simulations to study the global effects of cosmic rays. And so the basic picture is cosmic rays are accelerated in galactic supernovae, at least again, these are low energy cosmic rays. They travel along tangled magnetic field lines before eventually being detected at or near the Earth. And basically, historically, all of the traditional scattering theories assume that along these magnetic field lines, there are a bunch of small scale fluctuations in the magnetic field that are of order the cosmic ray gyro radius, so roughly AU with, for the galactic conditions, that scatter the pitch angle of the cosmic ray they perturb it slightly, kind of continuously, which then leads to the observed dependence of the cosmic ray scattering rate on the cosmic ray rigidity. But the problem is, as it's become obvious, or as we've discovered in the very recent past, is that by requiring that these perturbations are continuous in the volume filling ISM, we actually run into some pretty fundamental problems that prevent us from being able to predict we run into some fundamental problems that prevent us from being able to reproduce the observed dependence of the cosmic ray scattering rate on the cosmic ray energy. And so in the last year or so, we've been thinking about a new way of thinking about cosmic ray scattering, where you still start out with the same assumptions and reproduce the same observables. So cosmic rays are accelerated in supernovae, they travel along magnetic field lines, but instead of being scattered a little bit everywhere, we're thinking about cosmic ray scattering as an intermittent process, where cosmic rays would be free streaming along magnetic fields most of the time. And then every mean free path of about 10 parsecs for a GeV cosmic ray, they would be scattered by some scattering structure, which is, could be a number of things, in which they are strongly scattered in a brief amount of time and then escape to continue free streaming until they're scattered again by another patch. And so we've spent some time in this recent paper that it's up on the archive, just submitted to MNRAS, where thinking about the physical properties that such scattering objects would need to have, and then thinking through kind of what those candidate structures might be and how we could potentially tell the difference observationally. And so that's something I'm going to be doing follow-up work while I'm here. And so if you're interested in this, please come talk to me afterwards. I'm looking forward to meeting you all. Thanks.
Hey, thank you, Iryna. Any questions? Greg.
Thanks. Can you comment about energetics? Is the cosmic ray gaining or losing energy in this process?
It might be, so they wouldn't be accelerated by these.
Right, that's what I wonder.
Yeah. I mean, I guess it could be like if this is a weak shock, that there might be some acceleration, but this is primarily for scattering and not necessarily
So it's just a trajectory change, no energetics.
Yeah.
Thanks.
Okay, and a question from Sandy.
Can you just say a few words about the observables and the probes that you use to constrain your models?
Yes. So the scattering ray. So there's a lot. Let me think about how to organize it. But so kind of some of the key observables are the spectrum of the cosmic rays that we detect. Also ratios of like primary to secondary cosmic rays and sorry, I'm blanking on the words that ions that decay, so we can kind of constrain how the cosmic ray kind of interactions with the ISM is a function of the cosmic ray energy and the species. But then on galactic scales, we think about looking at gamma ray emission and synchrotron emission to kind of probe how the cosmic rays interact with the actual like ISM. I don't know if that answered.
Yeah, so very important work. And so this traditional model you explained is based on this very crude assumption that in large scale, such same magnetic field or similar magnetic field can give you a similar large scale scattering of the particles. And your model of this patchy model is more realistic and showing the structures. Can you elaborate a little bit more how this intermittent model helps with the explanation of your distribution of the cosmic ray? Because from a very naive point of view, if it's a large scale distribution is not impacted by those models, why would this patchy structure help a lot in improving your explanation in those large scale structures?
Yeah, great question. So kind of the key problem with the traditional models is that by requiring the magnetic fluctuations to be volume filling, in order to reproduce the observed energy dependence, you need to impose a very specific kind of power spectrum of those fluctuations that is like challenging to explain theoretically, at least with the kind of current theories we have. And by having this patchy scattering model, we don't actually need the magnetic perturbations to have any specific spectrum. We can reproduce the same energy dependence by imposing a size distribution on these scattering structures.
And one last question from Roger.
Yeah, I think it's very similar to Kerr's, but let me try to say it in a slightly different way. It's a characteristic of fluid turbulence that it exhibits intermittency. It's nothing like a Gaussian process, which is what makes it so hard to describe. And I'm trying to understand whether your view, which I certainly subscribe to too, is that that what you're looking at is a sort of intermittency in a homogeneous turbulence, or discrete structures like Greg mentioned, you know, supernova remnant here, a stellar end there, and so on. And those are the scattering centers. So you're seeing it as something like homogeneous turbulence or as discrete astronomical objects.
Yeah, so this is much more of the intermittent turbulence kind of thing. So we kind of looked at a handful of kind of macroscopic objects like, you know, supernova remnants, you know, spiral arms, et cetera. And the ones we could think of, like, they don't seem to match the number densities we would need to explain the scattering. Although they certainly could be contributing, they're just not the primary kind of patchy scattering models. But it's probably something like either weak shocks or intermittence and turbulence, maybe tiny scale atomic structures, something along those lines.
Okay, well, let's thank Iryna and all of the speakers from this session again.